This is Louis, Henry, and John Piero is on his way. Basically, we're doing the CubeSat design for the FUNSAT competition for NASA. Basically, what we're going to be doing is designing a miniature satellite. Well, we consider it 3U, which is the far right image here. It's 30 centimeters high by 10 with a 10 by 10 base. It shows the other types of satellites that we can use in the competition. 1U, 2U, and 3U. The only difference is the height is 10 centimeters increasing for each one. Basically, what the competition encompasses is what we believe we're going to need to emphasize on to win is the payload and the subsystem or various subsystems that'll separate our design from the rest of the competition. What we're going to be focusing on is the solar sailing system, which we're going to be talking about a little bit later, and the structural design of our satellite. This is just a document that NASA provided us for previous projects from last year, just as a reference or guidelines to dimension the structure. Everything has to fit within the dimensions here, and it'll show the access port sizing and just generic dimensions here. This is our conceptual design. We have some items hidden just to emphasize on the shell. We have the solar sail is actually going to go in this compartment here, all the electronics on the top, and our payload on the bottom. We chose aluminum 6061 as the material just because of the high strength properties, and it's easily machinable, so we can modify the structure if necessary for weight reduction, and it's relatively inexpensive. And now we're going to talk about the solar sailing system.
Now the solar sailing system, what it is, actually, it is a sail. Just that instead of harnessing wind, we're harnessing sunlight. And sunlight, it isn't exactly that we're harnessing it. We're using the photons within the solar radiation as a means to allow to impact on a reflective surface. This impact imparts a small amount of force onto the sail, allowing the satellite to actually move forward. The material typically that's used is mylar, where we're going to go ahead and use Captain, as it is provides a higher tensile strength, and it has less of a temperature variation with the different type of temperature. And then we will have to use some type of deployment system to be able to deploy that sail. So just to go into some of the details, as you can see, the sun hits the solar sail on a reflective surface, and then it bounces off an angle of incidence. That, depending on the angle that the sail is actually facing, will determine how much thrust and how much force is actually giving the satellite to move. And also dictates whether or not the satellite will move out of orbit, or either increase the orbit or decrease the orbit. Based on our size, we're seeing more or less of an acceleration of 0.02 millimeters per second squared of an acceleration. It seems small, but our focus was never to make it fast. Our focus was to make sure that it had the capability of moving in and out of the orbit. And then I'll switch it over to Louis, who's going to talk more about the deployment system.
One thing we want to incorporate to our design is the deploy system. This you can find in the other design. This is gonna be it gives the ability to change the orbit of the satellite. You can see this can give you the picture that we need. The challenge here is we need to fit in order to move the orbit satellite. The total area of the solar cell is minimum is 10 meters squared. So we need to fit all this area inside this 10 by 10 by 15 centimeter. In all this inside that volume in the satellite. Go next. Here is the deployment design. We have a motor on top that moves the spindle in the center, and these booms are going to be rolled inside the motor. So at the end, the total diameter in the center of the plate is 90 millimeters. So that's the spindle with the booms. These booms, there are 4 of them. They're going to be attached to the cell on the corner. So when the motor moves the spindle on the center, the boom are going come out of the system straight, and the cell part, the cell are going to be falling in this part, and when the booms come out, it's going to be It's gonna be pulling the cell out of the compartment. This is just the mass and the cost. We consider for the material almost for the deploy system, all the materials are aluminum, and because of the weight and the harness, and for the booms we consider stainless steel, which is similar to the measure tape. For the payload, this is the camera. We're planning to take to incorporate 2 cameras, one on the bottom and one on the top of the satellite, because we want picture at day and at night. We want this, the position of the camera is gonna be below the solar cell, so the radiation from the sun doesn't affect the camera. So we want to take picture of the atmosphere, and with this camera we're gonna be able to measure the weather, the temperature, and high of the weather. This is just the batteries. This is just the components of the camera. And this is how I can buy it. Thank you.
That's it. Put a little question slide at the end there.
Yeah.
All right, could you go back to the structural design slide for me, please? One before that, let's see, yeah, that one. It looks like a busy slide. Could you do something about that, make things clear, or
We can enlarge the picture.
exactly enlarge the picture and put it on a separate slide, and then might even still be able to lower the font size and put that under a much larger view, just make it look clearer. And from a technical standpoint, I have no questions.
Do you have a timeline?
No, we need to incorporate that.